Welcome back. Wind turbines or windmills have been around for hundreds of years. The old-fashioned windmills were used for grinding grain and pumping water. The principles used for utilizing the energy in the wind were not very advanced. The modern version, the wind turbine, uses the same basic principles as airplane wings to convert the kinetic energy in the wind to rotational motion. This will be addressed later on. Now I will describe the name of some of the main components of the wind turbines. To the left on this slide, the most common offshore wind turbine is illustrated. It is called a horizontal axis wind turbine, as the rotor is rotating about an almost horizontal axis. However, various other turbine solutions are also available, as for example the two vertical axis turbines to the right. These are rotating about a vertical axis. One of the advantages of these designs is the possibility to have a generator located at the bottom of the tower, in contrast to the horizontal axis turbine, which has the generator at the top of the tower. In general, however, it has not been possible to obtain equally large efficiency for the vertical axis wind turbines as for the horizontal axis wind turbines. The three-bladed horizontal axis wind turbine is frequently denoted the Danish concept. It is not a law of nature that the horizontal axis wind turbine should have three blades. It could have fewer and it could have more blades. But there are several good reasons for using three blades. These are related to aerodynamic efficiency, dynamic properties, as well as cost issues. Now I will name some main components of the offshore wind turbine. At the top we have the rotor nacelle assembly. This consists of the rotor blades, the hub in which the rotor blades are mounted, and the nacelle. The connection between the hub and the rotor blades is such that the blades may be twisted or pitched. Thereby, the aerodynamic forces acting on the blades can be controlled. The nacelle is the machinery house in which all the components transforming the rotor motion into electrical power are located. Some of the key components are the drivetrain transmitting the rotor motion, a gear speeding up the rotational speed, the electrical generator, and various control systems. The rotor nacelle assembly is mounted on top of the tower. As the wind turbine always should head into the wind, the whole rotor nacelle assembly may rotate on top of the tower. The system performing the rotation is called the yaw system. The tower is mounted on top of a transition piece between the tower and the substructure. The transition piece is a consequence of the most common choice of substructure, the monopile, and the installation technique. The monopile is driven into the soil and the transition piece is mounted on top of the monopile. This makes it possible to install the tower vertically, even if the monopile is installed at some angle. On top of the transition piece, an access platform is located. During maintenance work, people enter this platform, and from there, they may access the interior of the tower and the nacelle. The structure below the transition piece and the seafloor is denoted the substructure. The most common design is a monopile or a vertical steel cylinder. This cylinder is driven into the sea bottom sediments. As The part below the seafloor is denoted the foundation. How long down into the sediments the monopile is driven depends upon the geotechnical properties of the sediments. I will come back to other possible substructures later. All components below the rotor nacelle assembly are together called the support structure. Here you see a simplistic view of the main components in the rotor nacelle assembly. For most state-of-the-art wind turbines, the rotor may run at varying speeds. As will be outlined in more detail later in the course, there exists an optimum range for the ratio between the speed of the rotor and the wind speed. This ratio is called the tip-spin ratio. This implies that most state-of-the-art offshore wind turbines have a tip speed at rated wind speed in the range 80 to 100 meters per second. This again implies further that the larger the diameter of the rotor, the lower is the rotational speed. For example, a 5 megawatt turbine has a rated rotational speed of about 12 revolutions per minute. This is too slow for a normal electrical generator. Therefore, a gear is introduced speeding up the rotational speed by a factor close to 100. Thus, the generator is running at close to 1200 revolutions per minute and can generate alternating current or AC current at about 40 Hz. But as the rotational speed is variable, a frequency converter must be introduced to secure a correct AC frequency and phase of the current delivered by the turbine. As the rated power of turbines increases, and with a corresponding increase in diameter, the rotational speed is reduced. For example, a 15 megawatt has a rated rotational speed of about 7.5 revolutions per minute. Using a gear between the rotor axis and the generator will thus require an almost doubling of the gear ratio as compared to the 5 megawatt turbine. For this reason, large state-of-the-art turbines frequently use a so-called direct drive permanent magnet generator. Such generators are mounted directly on the rotor axis. The generator has many magnetic poles along the periphery, securing a sufficient high frequency of the AC power. The direct drive machines have fewer mechanical parts than the geared machine. This is an advantage with respect to maintenance. But in general, the direct drive machines are heavier than the geared machines. A mixture of the two solutions have also been suggested, where a gear is introduced to increase the generator speed, but still use a multipole generator.